Bismillahirrahmanirrahim. Assalamu alaikum everyone. So today we will be having lecture number 24, right? And we will be discussing about circuit analysis, sequential circuit analysis, and in addition to design, right? So today regarding the analysis, we will be discussing sequential circuit analysis by signal tracing, right? And when we talk about the sequential circuit analysis regarding signal tracing, we will be assuming that we are analyzing clocked sequential circuits, right? So we have to go through certain number of steps. First, we have to make sure that all the flip-flops or memory elements, they are at the zero state, right? Mean we have to reset them, right? Or then we have to determine the input, right, and the output, right? So input regarding the input to the flip-flops, memory elements, and the output regarding the overall circuitry output. After that, we have to find out the next state, right? And that will be obtained on the next active clock edge, right? So we have to find out the states, right, regarding all the flip-flops on the arrival of the next clock pulse, right? Okay, and then after that, obviously we have to find out the new state, because after the arrival of that clock edge, right, there has to be certain changes or new states, right? So we have to find out the output that corresponds to the new state, right? And we will keep on going unless we have applied all the possible sequence, right? For example, if we have two values A and B, so we will be having 0 0 0 1 1 0 and 1 1, right? So these are the sequences which we will apply one by one, right? So let's have an example, right? We have an example of a serial adder, right? So you can say that this is the block diagram of a full adder, right? And we can see xi and yi, right? So these are the inputs, and this is carry in, ci, si, sum, right? So this is the sum, and as a result of addition of those two bits, corresponding bits, we have a sum and the carry, right? And you can see that this carry has to be stored here in this flip-flop that is clocked, and then this is applied as an input, right, to the full adder, right? So here, for example, if we have 4 bit number, right, and we have 1 1 0 1, right, and again we have 1 1, right, 0 1, right? So we have to add those numbers, and this represent x and this represent y, right? So what we need to do, we need to add the corresponding bits, right? So this is the bit at 0th position, right? So what we will be having, sum as 0, right, and we have a carry here. So that carry has to be stored here, right? And then on the arrival of the next clock pulse, that carry has to be applied here, right? So now what we will be doing, we will be adding those 3 bits, right? So now we are adding those 3 bits, right? Carry, right? And this is the bit at first position, and this is the second bit at the first position, right? x1, y1. Now we will be adding them all, right? So we have a sum 1, we don't have any carry, right? So you can see that we have the carry 0, right? So that carry has to be 0, and this 0 has to be propagated here, and now we'll be adding those 3 bits, right? 0, 1, 1, some 0, and again we have a carry here, right? That carry has to be moved here, and Q follows D, we all know, right? And then on the next clock those 3 bits will be added, right? So this is the functionality of the serial adder, right? And we have assumed that we have 2 numbers, 4 bit each, right? And we have to add them. Okay, as you know that here we have XI, YI, and CI, 3 inputs, right? So there are 8 different combinations starting from 0 to 7, right? 0, 0, 0 till 1, 1, 1, right? And then you can see that from this we can calculate the carry and the sum, right? So you can see 1, 1, carry 1, sum 0, 1, 1, 1, carry 1, and sum 1, right? So we have the truth table for this full adder, and this is something different we talked about, right? So this is the timing diagram, right, as we are analyzing the sequential circuit regarding the timing signals. So you can see we have a clock. This is the input Xi, this is the Yi, representing the 2 numbers that we have to add, and this is the carry in, carry out, and this is the sum, right? So you can calculate and you can see the timing diagram, right? So now we have to draw the state diagram from this truth table, right? So if I look here, right, so here we have 2 states, S0 and S1, right? So let me call S0, right? So here we have 0, 0, right? 0, 0, right? Where the CI positions or carry positions where we have 0, right? 0, 0, right? So you can see 0, 0, sum 0, right? So input, sum, that is output, right? 0, 1, sum 1, right? 1, 0, right? And we have sum 1, right? So here we have 1, 1, right? So you can see whenever we have 1, 1, right? So what we have to do, we have to move from this state to the next state, right? So here you can see that we have something different. So we have 1, 0, right? No carry, right? No carry and no carry out, right? So here we have carry out. So that's why this is somewhat different from those previous states, right? So here 0, 0, right? No carry out, 0, 1, sum 1, no carry out, 1, 0, no carry out, right? So whenever we have a carry out, so that is something different, and we have to move from this state that is the present state to the next state, right? So here we have S1. So if you look at S1, right, we have 0, 1, right? So let me put a cross here, 1, 0, cross here, 1, 1, cross here, right? So here we have, right, and you can see we have all ones, right? And again here we have 0, 0. This is the carry in, right? So we have carry in, right, for all crosses, right? So 1, 1, 1. So this is somewhat different, right? So here if I talk about this, right, so 0, 1, right, and you can see output sum is 0, right, and 1, 0, right, here sum 0, right, and here 1, 1, right, sum 1, right, and this is 1. So this is somewhat different, right? So here again we have 0, 0, right, but there is no carry out, right? So if I, right, so you can see we have some sort of symmetry, right? So in carry out we have all ones, right, regarding those rows, but here we have something different. So that's why we need to move from S1 to S0, right? So on 0, 0, these are the inputs, right? Corresponding bits, and this is the output, right? So you can see that we have sum 1. So that's why we move from S1 to S0, right? So this is the state diagram, right, regarding the serial adder. So these are some of the goals. Whenever we are analyzing a sequential circuit, right, we are interested in order to characterize the type of machine, either it is a melee machine or it is a Moore state machine, right? And another objective is to find out the state equation, right? So we know that state equation is a function of current state and the inputs, right? And then we have to find out the output equation, right? And again we have to characterize either melee or Moore, right? And we also need to mention the behavior, right? And for that we normally draw state table or the state diagram, right? So you can show the behavior of the circuitry by using the state table or state diagram, right? Okay, so let's talk about state reduction, right, and state assignment, right? So if I compare this with the combinational circuitry, right, so whenever we have a combinational circuitry, right, and we normally wish to have the combinational circuitry, right? So let me talk about the Boolean expression, right? Or we have a truth table and we have to define or draw a combinational circuit on the basis of that truth table, right? So what normally we do, we perform simplification, right? If we have a Boolean expression, we will apply Boolean laws or axioms in order to have the minimum expression, right? Or you can say in order to minimize the Boolean expression. But if you have a truth table, right, and you want to simplify, right, so what you normally do, you draw the truth table and you go through certain number of steps in sequence, right? First you draw all the truth table, right, onto the K-map, and then you look for different groupings, right, pairs, quads, squares, and so on and so forth, and after simplification you have the minimum number of gates in order to have the same functionality, right? So the goal is to reduce the number of gates that has been used in order to perform the same functionality, right? So whenever we talk about the sequential circuit design, so what we can do, we can reduce the number of states, right? So there are certain number of steps in order to do that, right? So we will see those steps in a couple of moments, right? So let's start the state reduction, right? There are, because our sequential circuitry, it is based on the memory element and the combinational logic, right? See, memory elements, they are based on the sequential logic, and the input function or the output function, they are actually based on the combinational logic, right? So here our objective is twofold, right? So on the one hand, we want to reduce the number of gates that has been used for the input or for the output. On the other hand, we want to reduce the number of flip-flops, right? So here you can see that we have a state diagram, right? And then we can have the reduction, right? Okay, so there are pros and cons, right? Advantages and disadvantages of doing the state reduction, right? So one of the advantage is that we can reduce the number of flip-flops, right, that are the memory elements and that represent the sequential logic, right. The disadvantage is that sometimes when we want to reduce the number of flip-flops, it may rise the number of combinational gates, right. So sometimes it can happen, right, or sometimes you reduce the number of flip-flops and your number of combinational gates, that doesn't change, right. So this is not the case for all the scenarios, right. So this is one of the disadvantage of having the state reduction, right. Or you can say that if you reduce few flip-flops, right, so as a result of that state reduction, right, you have to add more number of gates, or you have the size of your combinational circuitry, it increases, right, or the number of gates rises, right. So here we have an example, right. So you can see that we have a state diagram, right, and we have different circles mentioning the state, right. So in spite of putting the values, right, for state representation, we have named those different states, right. So you can see that we have different alphabets, A, B, C, D, E, F, G, right, and then we have certain arrows that shows the transitions, and we have different values mentioning the input and the output, right. So this is the state diagram, and we want to reduce the number of states. So this is the same state machine, state diagram, right. So one question we can ask, that either the reduction is possible or not, right, and we have to go through certain number of steps in order to achieve the minimization or state reduction, right. So you can draw the state table with the help of this state diagram, right. So if you have the state table, you can draw the state diagram. If we have the state diagram, we can always draw the state table, right. So this is the present state, and this is the next state, and this is the output, right. So here you can see x is equal to 0, x is equal to 1, right. So as I have mentioned, we have named those states, right. This is the present state for x is equal to 0, next state, and this is the output, right. So you can see we have present state, next state, and the output, right. And after getting the state table, right, so we need to look for similar states, right. So if I look at this row, so you can see we have present state E, A, F, right, output 0 and output 1, right, G, A, F, 0 and 1, right. So you can see we have AF, right, AF, right, 0, 1. So this is the next state, and this is the output, right. So you can see that this and this column, they are identical, they are the same, right. So it means that the states E and G are equivalent, right. So what we can do, we can remove G and replace this with E, right. So I can put an E over there, right. Okay, so what is next, right. So we have F, E, F, 0, 1. If I go back, right, so we can replace, so we have to remove G and replace this G with E, right. So you can see next F, E, F, 0, 1, right. So E, A, F, right. So as we are removing G, right, and we are replacing this G with E, right. So now what is next, right. So here if I look, right, again EF, right, this is next state, 0, 1, these are the outputs. This is the output column for x is equal to 0, and this is the output column for x is equal to 1, right. So EF, EF and 0, 1, they are same, right? The values are same, right? So it means D and F are equivalent. So what we can do, we can remove F and replace this with D, right? So here we have to remove what? F, right? And we have to replace a D, right? So here we have the resultant, right? So we have to remove F, right? And here we will be having D, right? So there is some more reduction possible, right? No, we don't have any further state reduction, right? So this is the state diagram we got from the state table directly, and after the simplification we have this reduced finite state machine, right? And we can verify the sequence, right? So this is the state, input and output, right? Right? And the next step is, right, we have to do the state assignment, right? So you can see we have the A, B, C, D, E, right? A, B, C, D, E, right? Now we are actually performing the state assignment, right? So state assignment 1, right? This is binary. Assignment 2, this is gray code, and this is assignment 3, right? So here you can see we have conventional binary combinations starting from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, right? And here we have gray code, only one bit will be changing at a moment, moving from one to another slot, right? So here 0, 0, 0, 0, 0, 1, 1, 1, right? And 1, 0, 1, 1, right? So these are the different assignments. And now we are moving from the analysis to the design, right? So we have to go through certain number of steps in order to have the design of sequential circuits, right? Like whenever we are performing the analysis, we follow certain number of steps. So similarly, whenever we are designing a sequential circuit, we have to go through certain number of steps. So here we have mentioned design of synchronous sequential circuits, right? So first we have to find out the state diagram, right? So next step is the minimization as in combinational logic, right? So we have to start from somewhere, either from the Boolean equation or from the truth table, right? Or from the circuit diagram, right? So here we have the state diagram, and after that in the combinational logic, if we have the Boolean expression, we have to perform the simplification by using Boolean laws, and we have the truth table, we have to perform the simplification by using K-map, right? So here we have to perform the same simplification by using some state reduction mechanism, right? So you have to look if it is possible you can do the state reduction, right? So after that we will be having the state table, right? And then state assignment, and then we have to choose the flip-flop, that what sort of flip-flop we are going to use, right? And after that we have to use the excitation table for the flip-flop which we have chosen, right? And after the excitation table we have to complete the table, right? And finally we have to draw the circuit diagram, right? So let's have an example, right? So we have to design a circuit that can recognize the sequence 1, 1, 0, 1, right? So there are few number of points which we have to keep in mind, right? Like if we have this string of zeros and ones, right? So you can see 1, 1, 1, 1, 1, 0, 1, right? It contains 1, 1, 0, 1, right? So if I, right, 1, 1, 0, 1 and 1, 1, right? right, and 1 1 is a proper subsequence, right. So it means, right, the circuitry, right, or the machine, it has to memorize that the first two ones have occurred, right, because we have the 1 1 as a proper subsequence, right. So it means that the machine has to memorize that the first two ones have occurred, right. And if we have this sequence, right, 1 1 0 1, right, and 1 0 1, right. So you can see if I, right, have this, right, and then I can have this, right. So you can see that this one is somewhat common between these two subsequences, right. So you can call this an overlap, right. So 1 1 0 1 and then 1 1 0 1, right. So this is an overlap, right. Okay, we have to start, right. So first we will be defining the states of the sequences, right, for recognition, right. So this is the first symbol, right, and then we continue through each symbol, right. So here you can see 1 has occurred and we have, this is input and this is output, and we have moved from A to B, right, and it means 1 has occurred, right. So output, right, so output 0 means that this combination has not occurred, right. Whenever we have 1 as output, so this is understood that the sequence has already been occurred, right, and we have recognized it as 1 1 0 1, right. So then we will continue, right, for each symbol, right. So we were here, if I go back, so we were here, right, and we already know that 1 has already been occurred, right. So after that we have another one, right, and we reached at C, right, and you can see the output. It means this combination has not been recognized or identified so far, right. And after 1 1 0, right, so if I take 1 1 0 and again 0, so we don't have this combination till now, right. And then after that you can see that we have the combination and 1 1 0 1, and this is somewhat different from 0, right. So as we said or mentioned that whenever we have 1 as an output, so it means that the combination has been recognized, right. So there are a few points which we have to take into account, right. So what like you can see that we have this combination, right. So this is a subsequence of 1 1 0 1, right, final one, right, 0 which is not a subsequence of 1 1 0 1, right. So it means it should represent the same state reached from the initial state after a first one is observed, right. So what we have 1 1 here at C, right, and you can have another transition, right, from D to B, right. So this is another transition, right, from D to B, right. No proper subsequence when we are at A, right. Subsequence 1 has occurred, we are at B, right. C, subsequence 1 1 has occurred, we are at C, right, and the subsequence 1 1 0 has occurred, right, so we are at D, right. So here you can see that we have, so 1 1 on the arc from D to B means that the last one has occurred, and thus the sequence is identified or now recognized, right? So this is the, and these are the, we all know that these are the transitions. The arrows or arcs, they represent the transitions, right? So these are the possible transitions, right? And here you can see that we have from D to 0 0, right? Right. And from this state diagram, what we have to do next, we have to fill the state table, right? So you can see that this is the present state, right? And then we have the next state, right? And we have the output, right? So A, and next state is A whenever we have x is equal to 0, right? And whenever we have x equal to 1, we are at B, we have moved to B, right? And these are the outputs, right? X is equal to 0, we have 0, x is equal to 1, we have 1, right? And we have filled the state table, right? And now we have to identify the type of the machine, either Moore machine or Mealy machine, right? Right. So here you can see that this is sort of Moore model, right? Because the output is dependent on the current state only, right? Right. So this is a sort of Moore model, right? And then next, what we will be doing, we will be having the state assignment, right? So these are the present states, right? And this is next state, and this is the output, right? So 0 0 0 1 1 0 1 1, right? So again here we have another state assignment, right? So now we have used gray code assignment 0 0 0 1 1 1 and 1 0, right? So you can see the difference. If I go back, so here we have 0 1 1 0, over here we have 1 1, and then after that we have 1 0 because of gray code assignment. And then what we need to do, right? So we have to choose the flip-flop, right? So we have chosen over here D flip-flop, right? And we have two right, flip-flops, right? So or you can say that we have 4 states. If I go back, so we have 4 states and we need 2 flip-flops, D flip-flops, right? And then we will be drawing the K-map for DA, DB and Z, right? So this is the flip-flop, and this is the tagging for the flip-flop, A flip-flop, this is B flip-flop, right? So here you can see I have to draw this, right? This state table, right? So you can draw the K-map, right? And after drawing the K-map, we will be looking for the combinations or groups, right? So here we are looking for pairs, right? So this is one pair, right? And this is the second pair, right? So as a result of this pair, we have, right? So you can see that we have what? We have BX, right? As a result of this pair, we have what? We have AB, right? So for DB, you can see we have a square, right? So we have a X. For Z, we have only one, right? So we have A B bar X, right? So this is the one, only one, right? So A B bar X, right? And after that, what we need to do, we need to plot the circuit, right? So you can see for the A, you can see this is the input to the flip-flop, right? So this is A. I will write down the expressions, right? So this is what? A, right? B, and then we have BX, right? So I have AB plus BX, right? So this is for DA, right? For DB, we have X, right? So you can see we have X. For Z, this is A, And where is B bar? So this is B bar, and this is what? Where is X? Right, this is X, right? So A, B bar X, right? So this is the circuitry, right? And that circuitry is doing what? It is recognizing this state, right? So whenever we have 1 1 0 1, we will be having, right, a 1 at the output, right? So this is the output. Okay, right? So now we have another example. So here we have to design a 3-bit counter, right? So as mentioned, 3-bit counter. So how many values we can have? 0 0 0, starting from 0 0 0, 0 0 1, right, and so forth. So you can see that we have, so then this will be counting forever, starting from 0 0 0, right? So it will start from 0 0, right? 0 0 1, 0 1 0, and then we have 1 1 0, right? 1 0 0, 1 0 1, 1 1 0, right? 1 1 1, right? And after 1 1 1, what we will be having? We have all zeros, right? So it will be oscillating all the time, right? So here you can see, right? So we start from 0 0 0 0 1, and after 1 1 1, we have 0 0 0 on the next clock, right? Okay. So we need state table, right? So these are the present states and these are the next state, right? So you can see that if we have a clock here, right? So this is the present state, and on the arrival of the clock, this is the next state, right? And then we have 1, right? So this is the next state, right? So here after 1 1 1, we have next state as 0 0 0. Right? So next we will be choosing, because there is no possibility of state reduction, right? Right? So we next have to choose the flip-flop, right? So what we are choosing, right? So we have chosen T flip-flop, right? And this is the excitation table for T flip-flop. You can see we have next state, right? And this is T, and this is the operation or comments, right? So present state, when we have T0, right, no change. We have T1, we have the next state, right, complement. So present state, next state, and these are the flip-flop inputs, right? So you can see we have right, if I go back, right, so we already have the equation for the T flip-flop, right? So we have to put the values there, and we will be having the state table, right, in order to calculate the inputs, right? So and next we have to draw the K-map for simplification, right? So you can see that this is the simplification regarding the combinational logic, right? So we have A1 A0, right? We have taken here along the horizontal axis, and for the vertical axis I have taken A2, A0, A1, A2, right? So these are the, so for TA2, right, so we have this expression. For TA1 we have this expression, and for TA0 we have this expression, right? So I will be having this, right? So TA2, right? So where is TA2? So we have only 2 1s, right? If I have to write here M0, M1, M2, M3, M4, M5, M6, and M7, right? So you can see that we have 1 at M3 and then 1 at M7, right, regarding the TA2. For TA1 we have M1, right, M3, right, this is M3, and this is what, M5, this is M7, right. So we have straight away a square. As a result of this grouping, right, or a square, we have A0, right, for TA0, right, we have all ones, right. So we are left with a quad, right, 1 2 3 4, and this is a quad, right. So we are having 1, and this is the circuitry, right. So as I have mentioned that we have to use the T flip-flop, so you can see that this is TA0, right, 1 TA1, right. So TA1 A0, so this A0 is acting as an input to the TA1, right, TA2 A1 A0, right. So where is A0, right, and this is A1, and this is the clock for all the T flip-flops, right. So they are clocked with the same clock, right. So when we talk about the sequential circuit design, right, so we have to think about the combinational as well as the sequential logic part, right. So the sequential logic is normally based on the flip-flops, right, and the combinational logic is based on the digital gates, right, conventional digital gates, right. So here we have another example, right. So let's talk about sequential circuit design, right. So here we have a flip-flop, right, JK flip-flop, right, and we have the truth table, right. So here you can see that we have all possible combinations for J and K because we have two inputs, right, J and K. So we have 4 different combinations, and this Qn is mentioning the present state or current state, and this Qn plus 1, right, is indicating the next state, right, or sometimes in literature you will see Qt and Qt plus 1, right. So Qt mentioning the current state or present state, and Qt plus 1 is indicating the next state, right. So here you can see that we have 0 0, current state 0, and next state will be 0 0 0, current state 1, and next state will be 1, right. So whenever we have 0 1, current state 0, and the next state is also 0 0 1, current state 1, and we have next state as 0, right. So here again we have 0 0, right, and 1 0, right, current state 0, and we have 1, right, 1 0, current state 1, and we have 1, right. So it means here you can see that we have next state 1 in both cases, right, 1 1, right. And if we have present state or current state 0, so it has to toggle, next state is 0, and if we have 1 1 and the current state is 1, we have 0, right. So there is a toggle, right. So here what I did, I constructed the excitation table for JK flip-flop, right. So you can see we have column for states, this is the present state and this is the current state, and these are the possible JKs, right, values. So you can see if I, right, look for zeros, right, so you can see that for those zeros, right, JK 0 0, right, and here we have 0 1. So J remains 0, but K can be either 0 or 1, right. So what I can do, I can place a D mentioning don't care, right. So you can place a 0 or a 1, right. And for 0 1, right, so here we have 0 1, right. So let me put a cross here, and where is another 0 1, right. So I put a cross, or you can also see the arrow with different color, right. For this 0 1, you can see we have J K 1 0, right. So this is 1 1, right. So here K remains 1, right, 0 1, right, so 0 1 0 1, right. So you can see J and J, right, 1, but we have K0 or K1, right. So again we can put D here mentioning don't care, right, and then we will be looking for 1 0, right. So where is 1 0, right. So this is 1 0 mentioned with the green arrow, right. So this is 1 0. So let me put a different sign here. Where is 1 0? So I will put a different sign, right. You can also have the arrow, green arrow, right. So 1 0 1 0. So K remains the same, but J can either be 0 or it can be 1, right. So here we have a D at J, right, for 1 1, right. So where is 1 1, right. So you can have 1 1 here, and we have another 1 1 here, right. So for 1 1, right, here and here. So you can see K remains the same and J can be 1 or 0. So we have, right, so K remains the same and J can be either 0 or 1. So we have placed a D mentioning don't cares, right. So this is the excitation table, and you can see we have deduced, right, the excitation table from JK flip-flop truth table, right. You can do this for all other flip-flops, that includes D flip-flop and T flip-flop, right. And then what we can do, right, regarding the sequential circuit design, right, we can have the table, right, mentioning the current state, next state, right, current state, or you can name it the present state, and then the input for the flip-flops, right. So as we have JK here, so we have mentioned JK flip-flop inputs, right. So you can see we have 3 different values, right, ABC. So we have to mention JA, KA, JB, KB, JC. So this first letter is mentioning the flip-flop, type of flip-flop, and the second letter is the number, unique number, right, alphabet, mentioning the flip-flop, right. So here then what we can do, right. So for example, if you have to design a counter, right, binary counter, because before we have designed a 3-bit binary counter by using T flip-flops. So here if we have to design a 3-bit binary counter by using JK flip-flops, right, so you can say that we need 3 flip-flops, right, and same is the case for this table, right. So we need 3 pair of JK inputs, right. So this is the table, right, this is the same table which we have before, and these are the inputs for the flip-flops, right. And after having this table, you can call it design table, we can have this simplification, because these are the inputs to the flip-flops, right, and those inputs can be simplified by using gate map, right. So here we have JA, right, so you can see we have JA, so this is the only one, right, and others are don't care, right. So we can have this pair. So for KA we have BC. For if I look for JB, right, so we have 1 1 and other are don't cares, right. So 1 1, so we have a scare as a result of this grouping, right. So after simplification for JB we have C, and again for KB, right, so you can see we have 2 1s and all right, and then we have D's, don't cares, mentioning don't cares, right. So here KB is equal to C, right, and for JC you can see that for JC we have 1 1 1 1, and all the rest of the inputs, right, for this column are don't care, right? So you can see we have a quad here, hence we will be having a 1, and similar is the case for KC, right? So we have a quad, KC is equal to 1, right? So this is the circuitry, sequential circuit design, and you can name it a 3-bit binary counter, right? So you can see this is the present state, 0 0, right? 0 0 1, 0 0 1, right? 0 1 0. So this is the present state, and this is the next, and that next state is the present state for next clock, right? And this is the circuit diagram, right? And you can see we have 3 flip-flops, right? And here we have something different. As a result of this bubble, we have the active low, right? So falling edge will be working here. So A, B, C, right? So if I go back, right? So we have KA, BC, right? So here for KA, you can see we have BC, right? And for JA, we have BC, right? So we have the same input for this JK flip-flop, and then we have ones here, right? Right? So that's all for today's lecture, right? So today we talked about sequential circuit analysis, right, by signal tracing, right? And then we talked about sequential circuit design and how we can reduce the number of states, because in combinational logic we normally use Boolean axioms, Boolean laws, K-map, right? So here we can achieve the simplification by state reduction, right? So there are different pros and cons that are associated with that state reduction, right? So we discussed those different pros and cons, and then we have gone through certain number of design examples, right? So that's all. मेरी तरफ से अल्लाह हाफिज़, अस्सलाम वालेकुम.